Welcome to Aquaponics Academy, a bright agrotech podcast designed to help you overcome common aquaponic issues, learn new growing techniques, and help you be as successful as you can be as an aquaponic practitioner. Whether you're just getting started or you've been growing aquaponically for decades, this podcast is for anyone wanting to design the best performing system possible. Join aquaponics expert Dr. Nate Story, the creator of Zip Grow Towers, as he breaks down complex topics into easy to understand information. And now, here's Dr. Nate Story.
Hey, this is Dr. Nate Story with Bright Agrotech, and today we're going to discuss microbes. This is Aquaponics Academy, episode 19. We're going to talk about microbes and the role they play in your system, whether it's mineralization, nitrification, anaerobic versus aerobic mineralization. We're going to talk about all these things. We're not going to go into too much detail, but we're going to get into enough detail that you're going to be able to go out and find all of the information you need to understand your system a little bit better. So, microbes, why are they important? Well, a lot of people give lip service to microbes, but they end up spending all their time talking about plants, talking about fish, talking about these other parts of the system. In reality, when we talk about aquaponic systems, what we're really talking about is microbial systems. They are the heart, they are the soul of the system. An aquaponic system is basically a microbial system that supports fish, or on the other hand, a microbial system that supports plants. At the end of the day, they're all working together, but if the plants go away, the fish and the microbes can survive and do all right for a while. If the fish go away, the microbes and the plants can survive for a while. But if the microbes go away, everything dies. So, at the end of the day, microbes are the most important part of any mature, productive aquaponic system. So, how do microbes impact nutrition? Well, they absorb nutrients, they release nutrients, they free nutrients from organic compounds. This is called mineralization. They nitrify, which is an oxidation reaction, taking ammonium and oxidizing it to nitrate. And they pretty much are just involved in all of the nutrient cycling within the system. They're an incredible part of the entire nutrient cycle. So why do they do this? Well, microbes basically are engaged in the constant trade of electrons. Now, if we talk about, big, strong mammals like us, or elephants or whales or what have you, everything is engaged in the trade of electrons. But microbes do this on a much more fundamental basis. And so everything that they're doing is to basically harvest electrons from other compounds. Now, they're taking in some of these. They're absorbing, of course, phosphates. They're absorbing proteins and amino acids. They're taking those in. They're breaking them down and using them in certain ways. But at the end of the day, they don't necessarily get energy, or many of them don't necessarily get energy from that. These are an incredibly diverse type of organism. So when we talk about microbes, really, whether we're talking about, prokaryotic bacteria, which is what we're talking about most of the time, we're talking about a lot of different kinds of bacteria that do a lot of different things. And so it's really not very accurate, I guess, for me to make broad generalizations about them. But for most of the decomposers, for most of the bacteria in our systems that take organic matter and break them down, they're doing it to harvest electrons and to basically gain some nutrients or steal some nutrients from the material. So they're doing it to serve their own ends, for their own growth and reproduction. But in the end, it ends up serving the needs of the system because they're taking something that's not soluble, that's not plant available, and they're breaking it down. Or they're taking something that's toxic to the fish, and they're oxidizing it and turning it into a different chemical compound that isn't dangerous to the fish at all. So microbes have really special relationships with the different parts of our aquaponic systems. Whether it's the plants, they form very specialized relationships with the plant roots, trading different things for things with the plant, or taking plant compounds and breaking them down. Plants do a lot of dirty work themselves, but microbes do a lot of the work in the systems. Plants can't take organic compounds and break them down. They can't take proteins and break them down into ammonia or amino acids and then ammonia, but microbes can. And so they form very interesting relationships with plants and also with fish. In the same way, we talk about our normal flora. We talk about the bacteria that colonize our bodies and how important they are to our health. It's the same way with fish. Every organism in the world has evolved in conjunction with really, really diverse and complementary bacterial populations. And that's true of fish, that's true of plants, that's true of every multicelled organism on this planet. Without bacteria, we would all die. Nothing would survive. Bacteria are really at the core of everything. So microbes are out there. They're breaking things down. This is called mineralization typically. And mineralization is basically taking an organic compound. That is a compound that, may have some nitrogen in it or some phosphorus in it. And they're taking it and they're breaking it down into more fundamental things. Ultimately, we go from things like proteins with nitrogen, proteins to amino acids, and amino acids to ammonia. And then these microbes, nitrifiers, take over and they oxidize ammonia into nitrate. And so they're taking something that the plant can't use and they're making it available. And they mineralize a lot of different things. It's not just about, breaking down nitrogen containing organic compounds. It's about breaking down compounds that contain phosphorus, that contain potassium, that contain all of the other plant nutrients that we've talked about, and breaking them down in a way that makes them plant available, mineralizing them. Now, when we talk about organic versus inorganic, it's a really important distinction to make, because once something becomes mineralized and, like the rock around us, a lot of that was created by biology through mineralization. And so there's this constant kind of contribution that they're making towards, taking minerals or taking inorganic things and combining them with carbon to make them organic compounds, and then back and forth, mineralizing and creating these organic compounds, and then mineralizing and creating organic compounds. And it's really an amazing thing. It's shaped the world. It's shaped the ground that we walk on. And it certainly shapes things in our systems. So there's a couple types of mineralization. There's mineralization that takes place in aerobic environments and mineralization that takes place in anaerobic environments. And that's really important to understand too, because most people go for super aerobic environments in their systems, but there are some nutrients that only become bioavailable through anaerobic mineralization. So this is basically carbon compounds in an anaerobic environment, and the mineralized product, so if we're talking about iron, is reduced. And if you guys remember back to the iron episode, or if you've watched the YouTube video on iron, you remember that when iron is reduced, it's soluble. But then when it's exposed to oxygen, once it's oxidized, it becomes insoluble. It combines with other compounds, usually in the solution, and it precipitates out. It becomes a solid. And that's a bad thing. But if we want to see an actual iron cycle within our system, we need a little anaerobic activity. Now, it's not something that we want to encourage all the time. And remember that there are little teeny tiny microscopic anaerobic zones in a lot of parts of our system that we are never really able to see. But it is important to know that anaerobic decomposition, the mineralization that takes place in anaerobic zones, contributes to the overall health of the system when it comes to certain nutrients. So that's just kind of a side point, but it's good to note that a lot of these bacteria function in anaerobic environments. Some of them function in aerobic environments, and some of them function in both. So they operate in a lot of different little habitats and a lot of different types of environments, but the net result is they take organic compounds and they make them plant available. So otherwise, we just end up with all that fish waste just accumulating, and it would never break down. It would never be destroyed. Another side note is that redworms play a big role in a lot of people's systems. They're not necessary, but they can help speed this cycle up. And it's interesting to note that redworms function like little bioreactors. So they're not actually doing anything, right? They're feeding, I guess, but really all they are is a delivery system for all of their gut microbes, because they go through and they eat certain types of waste, or they cruise through and they just gobble everything up and they deliver it to the microbes in their gut. And in that contained and very highly moderated environment down there, those microbes will break stuff down and the worm will poop it out, worm castings, right? And the interesting thing is that the amount of plant water-soluble nutrients in that waste is much higher than we get through other decomposition reactions. And it happens very fast. So redworms can play a great role in speeding up certain nutrient cycles. Of course, they are consuming some of that energy themselves, so they're adding biomass. But that's not a bad thing either. They grow, they die, they release protein, ammonia. Becomes ammonia. It's oxidized to nitrate. It's all part of the circle of life in these aquaponic systems. So microbes, we know that they interact with the fish. They colonize the fish. They help the fish survive. They oxidize ammonia. We know they help the plants by making all of these carbon-based compounds available to the plants. But they also help each other. Microbes interact in very rich and diverse ways. And they interact with each other. They form their own kind of ecology within the system. And that's really important to know. A lot of people ask why their system crashes after they disturb it. A lot of the times because you disturbed that ecology. That ecology of microbes. And things like nitrifiers, they do not like UV light. So you go out and you turn over your beds in the middle of the day, and that UV light just zaps all of your nitrifiers, and all of a sudden your nitrification plummets, it crashes, right? And you have ammonia build up and your fish get stressed, and then things just spiral out of control. So it's important to understand that these organisms, they interact with each other in really unique ways, and they form really rich and diverse ecologies. And that's important to know because when we disturb those ecologies, we disturb the fundamental function of the system. And by fundamental, I mean at its most basic level, the bacteria that drive the system forward. They die, they're shocked, they slow down, they stop. You can do this by changing the temperature of the system suddenly changing the pH. As a side note here, a lot of people advocate high pH. You guys know that I advocate low pH in systems. You just got to take them there slowly because microbes are sensitive. Yeah, if you crash your pH, if you drop it suddenly, your nitrification is going to hurt, right? Because it takes them a little while to catch up. If you raise it, it happens the same way. It's usually a little less pronounced if you jack your pH way up there because, it's a little bit more friendly towards that reaction, the chemical reaction itself at higher pH. But, what we're talking about, there's changing system variables very quickly, and it impacts all of the microbes that do the work for us. So when we change our system variables, all of a sudden, change temperature, change light levels, change, oxygen or CO2 levels, change water flow, change these things, we end up with big changes in our microbial community, and not always positive ones. So we're searching there for trying to give our microbes the most steady, predictable habitat possible. And if we can achieve that, then we end up with really stable systems and over time with really productive systems. Now, the interesting thing that you need to keep in mind with all of this is as you start to think more about the microbial ecology of your system, as you think about what you need to give to these microbes, you need to remember that they consume a lot of things. So they're consuming typically a lot of CO2. So as CO2 is released into solution, a lot of these microbes are taking it up. They need CO2, dissolved CO2 in the water. It's not just algae, it's the bacteria as well. They need carbon compounds to break down. Nitrifiers need ammonia. These are just fundamental needs. And without that stuff, they won't always die, but they certainly slow down and they stop growing and they stop doing the work that you want them to do. But one thing that they definitely need, almost all of them, is oxygen. With the exception of some of our anaerobic mineralizing bacteria, oxygen is kind of the common ingredient for all of these other microbes. And the thing to remember is as they perform these functions, as they do the work that we want them to do, they consume a lot of oxygen. So when you are adding more microbes to your system, you really need to think about it as you're basically cashing in a lot of your oxygen credits. You're taking a lot of oxygen out of solution. That's fine if you can deliver more, but if you can't deliver more oxygen, you have the potential to really impact your system negatively. So an example of this is using like compost teas in your system. A lot of people will use compost teas, and I don't recommend it unless you're kind of advanced and you've been doing it for a while, you know the effects, you know how to kind of manage it, then it's fine. But for a lot of growers who haven't done this kind of thing before, adding compost tea to your system can crash your oxygen. So it can kill your fish. It can cause, some of your dieback of plant roots if you're in a raft system, something like that. Because what you're adding is a lot of organic material to the system. And when you add that organic material, all of the microbes go bonkers and they start to break it down and they start to consume oxygen to do that. So you can actually crash your oxygen. And, it's funny, I've proposed a couple of projects for refineries for bioremediation of wastewater from refineries. And refineries rely a lot on precipitating out certain like bad chemicals, right? So heavy metals, that kind of thing, they remove them through precipitation. But they have to make the water really anaerobic. That means they have to remove all of the oxygen from the water to do that with some of these things. And the cool thing is in order to do this, a lot of the time what they're doing is they're fostering a microbial reaction in the system that causes those microbes to consume all of the oxygen. So they'll add nutrients to the system. And then the microbes will consume all of those nutrients, consume all of the dissolved oxygen, and actually cause the water to go anaerobic. And it's really the most efficient way to do it. Nothing removes oxygen more effectively than really robust microbial communities just consuming it hand over fist. And when that happens, it causes the water to go anaerobic and causes a lot of those bad minerals to precipitate out. Where they can be removed, right? So removing selenium or some of these other soluble heavy metals. But that's an interesting thing to note because for aquaponic growers, it means that you need to always kind of keep your eye on your microbial activity and understand how adding things to your system impacts that. Understand that when you feed fish, they can be oxygen starved if you overfeed them, right? Because what's happening in their gut? You've got all of these microbes breaking down that food, breaking down all of that fish feed, all of the excess feed gets broken down, all of this stuff. You're not just looking at a bump in ammonia, right? Because we always see that after a feeding cycle. We always see a little bump in ammonia, but what we're also seeing is a drop in our oxygen. And that can be really, really dangerous for systems. Now, once you're stable and steady and you're feeding the same amount every day and your fish are kind of consuming slow and steady, we don't see these big fluctuations in dissolved oxygen. But when you're first starting out, it's something to keep in mind, especially for first-time growers who tend to overfeed. You can really, really impact your dissolved oxygen negatively by overfeeding. Anytime we add carbon to the system, anytime we add something that the microbes like to chew on, like to eat, like to decompose, we are impacting our O2, and we need to keep that in mind. And if you don't have an O2 meter, if you think you might be suffering from a lack of dissolved oxygen, then it's always good to have supplemental aeration, to turn your pumps up, to drain your beds, or to just kind of come up with creative ways to introduce more oxygen to the system. So oxygen and microbes have a fraught relationship. And remember, anytime you add carbon to your system, you will be consuming a lot of oxygen. So microbes also impact pH. Really, they're the main driver of pH. And in our aquaponic systems, it's mostly nitrification reactions that drive pH. But there are other mineralization reactions that are releasing hydrogen ions into the system that are acidifying solution. And so there's all sorts of interesting and complicated things happening in our systems that tend to drive pH down unless we've got a lot of carbonates. But it is good to note that for those who struggle with pH control, microbes are typically the solution and the curse. So think about how you're managing your microbes before you go and start adding bases or start adding acids. think very long and hard about how you want to manage pH on a microbial level, and think really hard about how you can change the variables in a way that means you can manage your pH on a more basic kind of day-to-day management level. Now, if you're going for big numbers, big production numbers, you can't always do that, right? If you're going for big production numbers, I almost guarantee you that you're going to be adding a base on a daily basis at some point, almost no matter where you're at and the hardness of your water. There are some waters that are just really hard that you can never, you're always introducing more carbonate than you can burn up through nitrification. But in aggressive systems and systems that are run with a lot of biological surface area and really heavy rates of nitrification and really fast rates of uptake by your plants, then you can usually beat your carbonate loading with nitrification. But anyways, getting back to the subject here, pH is primarily driven by microbes in the system. Your source water is always going to have pH, right? It's going to come in, but it's not going to be static. It's going to be dynamic. And the microbes are going to be the ones that are really changing that pH. So another thing to think about is temperature, right? And you might say, oh, microbes can't change the temperature of solution. And that's kind of true. I mean, that's 99% true, right? Remember that a lot of these reactions are either creating heat, right? A lot of them create heat, right? As the microbes decompose things. So heat is often generated, but it's not enough to affect your overall system temperature, to my knowledge. I mean, I don't know. People haven't really looked at that too closely, I don't think. It would definitely be worth looking at. I'm glad I started thinking about that. That's actually kind of an interesting question that someone should probably answer. But, temperature does have an effect on the speed of reactions. So a lot of these microbes are accomplishing these reactions with enzymes, right? And if you guys remember back to 9th grade science, enzymes basically speed up a chemical reaction. They're kind of a key to unlocking speed in chemical reactions. And enzymes are incredibly awesome little things that are used throughout nature, and microbes use enzymes to do a lot of these really complicated chemical reactions that would take forever if enzymes weren't being used. So how does temperature impact that? Well, typically temperature slows it down. Now, there's a balance here, right? Because as temperature goes up, oxygen becomes less soluble in our water. So as our temperature goes up, there's less oxygen for the microbes to consume. That slows them down. But as temperature goes up, enzymatic reactions typically increase. That's not always true, but by and large, as we see our temperature of our solutions kind of within the range of what's biologically reasonable here, as they go up, our enzymatic reactions speed up. And so there's kind of that sweet spot as oxygen is coming down, solubility of oxygen is coming down. As the temperature rises, and enzymatic reactions are increasing in speed as temperature rises. Kind of that crossing point is where we want to shoot for with most of this stuff. The place where we can accomplish that breakdown quickly, but not so quickly that we're consuming too much oxygen or taking away from our fish or from our plants. And we can always be supplementing oxygen. It's not a static thing. There's always oxygen diffusing into the water. But it is something to keep in mind as we think about temperature and maximizing both the breakdown of all of these organic compounds going into the system, trying to keep our fish growing and going fast, trying to keep oxygen soluble, trying to do all of these different things because they're not they don't always work together very nicely. Sometimes things are in conflict. And so as a manager, you have to think very carefully about how you want to do things, and you have to be very observant and make sure that you're not crossing the line or impacting any one part of your system too negatively. So that's about it for today. That's about as much as I want to cover. I don't even know how long I've been going here, but probably too long. So I'll leave it at that for now. Hopefully that's a little food for thought. If you guys have any questions about this stuff, we love to chat with you. And so feel free to give us a call, shoot us an email, contact us in some way. We want to hear about what you're doing. And You can read more about these microbes. You can read about nutrients in your aquaponic system, decomposition on the Bright Agrotech blog. And that's at zipgrow.com. We're on our YouTube channel. We're always posting great content over on YouTube. So check that out again. That's zipgrow, zipgrow.com. That will take you to our homepage. Lots of free resources, lots of helpful things, guides, you name it there, as well as blog posts on these Aquaponic Academy episodes and the topics that we cover. Check that out. Check out our YouTube channel. Thanks so much for tuning into this episode of Aquaponics Academy. On behalf of everyone here at Bright Agrotech, we hope you'll continue to join us for future episodes as we continue to give you the best information possible on aquaponics and creating a successful system. So there you have it. We talked a little bit about microbes today, about what they do in your system, why they're important to fish, why they're important to plants, and most importantly, why you should be thinking about microbes when you do anything regarding your system, changing pH, changing temperature, adding food, you name it. They are at the heart of everything in these aquaponic systems. So keep that in mind next time you go out to feed your fish or to do something strange. Just think really long and hard about how what you're doing may impact your microbial communities and as a result, impact your overall system health.